Hello, my name is Raymond Kang,
My name is Jerry Yang.
and we will be presenting our ECS 171 machine learning project, which is titled Predicting California Housing Prices. So these are our team members and the roles they played in this project. Problem statement. People are selling houses because housing is becoming expensive due to inflation, as seen in the figures on the right of the slide. Home sales are its highest peak since 2005. So our goal of this project was to use machine learning models to develop a model that can predict California housing prices such values based on historical data. This model will help users make efficient decisions about their personal measures of real estate. Since this model predicts housing values in California, it could be implemented by analyzing the data and summary statistics from a particular California district with the attributes the dataset provides. Thus, the clustering model will be used during this project. By clustering given attributes into different pricing segments and predicting the proportion of house values based on a labeled dataset, we will be able to implement our model to accurately predict the value of a house in California.
Before starting our own project, we look at many examples, hoping to find a suitable machine learning algorithm. We also want to understand the important factors that affect house prices. In the research, we found that these two algorithms have different advantages on this topic. The first one is the L1 and L2 regression. Using Ridge and Lasso can adapt to the data at hand, be used to include regularization parameters, reduce model complexity, and prevent overfitting. And for random forest, it has the lowest error in Tron's model. In John's research, he mentioned that the most influential factors are residential model factors, which include residence, usability, and numbers of rooms. And considering that families often look to purchase housing, we believe that school availability and quality surrounding the house is another important factor that helps determine housing price.
Okay, dataset preprocessing. On the left is our original dataset from Kaggle/Zillow, and on the right is our dataset after all the data preprocessing. So the dataset for California housing prices in 2020 come with a lot of features. There are about 31,000 row such houses and 41 columns, which were the label such attributes. However, many of the columns were removed due to poor correlation or irrelevancy. The original dataset came with multiple different housing types, so we removed rows in which the housing type was not single family, as our research was to predict the value of single family houses. Also, many columns such as cooling and heating were inconsistent due to the varying attributes, making it difficult to find a correlation with the listed value. The columns we decided as features to make in our model were bedrooms, bathrooms, total interior livable area, elementary school score, middle school score, high school score, tax assessed value, annual tax amount, latitude, longitude, which are derived from the original city label, and listed price. This left us with a total of 12 columns such labels in the data, 11 features, and 1 class. Dataset encoding. The values of cities were inconsistent in that each one was unique due to naming. So we used encoding techniques such as ordinal and one hot to encode the categorical variable city. However, this led to no correlation with the label listed price, which is the dependent variable. Therefore, we decided to use an API model to convert cities to numerical geographical coordinates, which were latitude and longitude. Methodologies. With the goal of predicting housing prices, we worked with regression models. To determine what features were used, we used the ones with the correlation coefficient with over a plus minus of 0.2, which was on the figure on the left, with the exception of longitude and latitude, as we believe that knowing the city coordinates should be important. The figure on the right is the process in which we as a team developed the application for this project. At first, we did collective research to find a data set. Then we split into front end and back end in their respective parts to eventually deploy a full stack application, which I will be demoing today. Models and results. For our solution, we decided to implement multivariate linear regression, and we addressed each linear assumption. We additionally implemented a simple L1 and L2 regression, Ridge and Lasso, as well as a cross-validated model. Finally, we implemented random forest regression. In addition to these models, we also attempted to make a logistic regression model. However, the accuracy was low and our problem was prediction, not classification. Linear assumptions. Linear regression is one of the most simple algorithms in machine learning. However, if most of the assumptions are not satisfied, the interpretations of the results can be invalid, hurting real world applications. For our MLR model, we use our preprocessed data to check the assumptions we thought were most crucial for our model and make a conclusion based on the results. The assumptions we decided to check are as follows: linearity, which assumes linear relationship between predictor and dependent variables. No linear relationship can cause extremely inaccurate predictions in an underfitting model. Normality of error terms, which assumes normal distributed error terms. A violation can inflate confidence intervals, once again leading to inaccurate predictions, and multicollinearity, which assumes predictors used in regression are not correlated with one another. Violation can cause issues with interpretation of model and its coefficients. Multivariate linear regression. We check for assumption 1 of linear regression by fitting a linear regression model to our split training/test data. The scatter plot depicts the relationship between our test set and the predicted values based on the fitted model. Based on the linear regression line, the general trend of the data and the calculated R-squared scored of about 58%, we can say that our linear model is subpar in predicting the listed prices in California housing. The score is not the worst, but the scatter indicates some variability. Actual versus predicted. The table and scatter plots show us actual house values against our predictions based on the linear model in our data set. Some differences are large, but this is somewhat expected due to the nature of the target variable and house listing prices being high to begin with. As seen in the scatter plot, many predicted and actual values overlap, but there is still a good amount of variability. Yet we still have a model that can be captured by linear regression, satisfying assumption 1. Normality of error terms. We use an Anderson-Darling test function for calculating residual/checking normality, which outputted an unacceptable p-value for assumption number 2 of linear regression. Based on the plot of residuals and non-normal distribution of residuals, assumption number 2 of linear regression is not satisfied with our model's data. While this is not ideal, we can continue checking for our last assumption, multicollinearity, and look for interaction effects. Multicollinearity. Performing a multicollinearity check is important as it tests for any interactions/correlations between the predicted variables themselves. Using the VIF library, we ran a multicollinearity check, taking all predictors into account, which is the table on the left. We can see that many of variables have a very high VIF value, meaning that they can be predicted by other independent variables in the dataset. Our next form of action was to attempt fixing the high VIF scores by using a function to combine correlated variables and dropping the others to predict listed price for future models. This not only produced a cleaner dataset, but eventually provided us with a more accurate model. The table on the right shows the output of combined variables and their respective VIF scores, which is now a lot lower. So the new R-squared. By using the same plots and charts as before, we were able to analyze the performance of our new model with our improvised dataset. Our model now has an accuracy score of 0.64, which is quite better than our original model score of 0.58. Additionally, many residual differences are also a lot smaller. However, a score of 0.64 can perhaps still be improved upon. As mentioned before, there could be an issue with how the weights for predicted variables are distributed, which somewhat improved with this new model. Yet we can see that a linear regression model may perform decently, but might not be enough to capture the model's trend. Simple L1 and L2 regression. As seen in our multicollinearity check, we can deduce that the features with a high VIF value likely will have very high coefficients. This implies that our dependent variable, listed price, would be significantly overpowered by those features, which can lead to overfitting. We can employ L1 and L2 regression to reduce model complexity and avoid overfitting. Our experimental results show very similar model/scores for both lasso and ridge techniques. While the scatter plots look extremely similar, they are not identical. Test data score is not rounded to show this. These models perform slightly better than our linear model, but the scores are not that much more impressive. L1 and L2 regression and extension. However, we decided to extend our L1 and L2 regression models by a bit by making use of the alpha argument in the regularization functions, as well as eventually using cross-validation to tune the alpha parameter. We initially generated an array of alpha values covering a full range of scenarios for our models. With the process of standardizing coefficients, we also plotted our alphas against their weights, with the expectation that larger values of alpha yield smaller coefficient estimates. As expected, this is the trend that the plot follows for both ridge and lasso regression. See the figures on the slide. Cross-validation model scores. From testing arbitrary alpha values to eventually using cross-validation for optimal alpha, we were able to come up with improved scores for one of the models, our ridge model. Our final score for each model after cross-validation is as follows. The ridge model had about a 0.7 score, and the lasso model had about a 0.58 score. Our final scores were also those that gave us the lowest mean squared error for our test data, which is interesting as our lasso model decreased in performance accuracy. Another interesting result we found was that the coefficient advantage Lasso seem to have despite its lower model score. According to online research of a similar model implementation, Lasso has a great advantage over rich regression in that the resulting coefficient estimates are sparse. Here we can see that 8 out of 10 coefficients are nearly reduced to 0, yet there exists a trade-off between sparse coefficients and a lower model accuracy score. All right, random forest. The random forest R-square test performed decently. However, we weren't able to track down what could be the reason for the performance score. We tried to use grid search CV to find the best parameters. However, with those new parameters, we had slightly worse performance. Demo. So our demo takes user input from the browser using the files app.js and index.html. Then it hits the endpoint to the backend server, which is run through app.py by pressing a button on the HTML page. The backend server makes a prediction using a pickle file of our model and returns the result to the front end. The front end then takes the response and displays it to the user in a results page. We will come back to the demo after finishing the slides. Conclusion and discussion. Our end model tends to predict a high price, which is better for sellers rather than consumers since they want to get as much profits for selling houses. So our model gives them a good starting point. We came to the conclusion that the significant differences between the different regions in California, that due to the significant differences between the different regions in California, it will be better to train a model on each specific region in order to get better predictions. These are our references. Thank you. Now I will show you a live demo of the project. So I will click on the link provided and navigate to the website. As you can see, our front end is beautiful, and we will press start to start the process. After clicking start, you can see the different categories of the houses pop up. So we'll enter some arbitrary values representing the values of these houses in 2020 into each of the categories. So let's say Los Angeles. Let's say there are 3 bedrooms, 2 bathrooms. The total interior livable area is 2,000 square feet. The elementary school score is 7. The middle school score is 6. The high school score is 8. The tax assessed value is about 1.65 million. And annual tax is about 20,000. And when I click the get result button, after a brief bit of loading, you should be able to see the predicted current housing value for a house with the attributes put in. So yeah, about $2.129812 million. I would like to thank my teammates for the wonderful work they have done on this project. And this concludes the presentation for our ECS 171 Machine Learning Predicting California Housing Prices project. Thank you.
Thank you.